I see there are a little bit less people in the room today, so I'll need your hands for a little while. First of all, a lot less people are interested in the underlying technologies that make consumer apps possible. So I want all of you to give a round of applause for yourselves because you're building the protocols and technologies that power the consumer apps. And secondly, I want again to thank Ansgar for his presentation and the amount of all of the work and effort that EF Research and Ansgar specifically puts into making Ethereum as efficient and as scalable, and the blockchain of the future is just insane. So another round of applause for Ansgar. So my talk will be split in two parts. In the first part, whereas Ansgar talked about the medium-term changes to Ethereum, I want to talk to you about Ethereum Endgame and how efficient and performant Ethereum could look like, where you could build a business enterprise-grade apps. And the second part, I want to bring you all back a little bit to the values that brought us into this industry in the first place. And one of these values is privacy, and how we can bring back privacy to Ethereum. So without further ado, I will need a little bit more of your time, and we'll do a little show of hands. First of all, how many people run Ethereum nodes? How many people use those nodes for RPCs? How many people run Ethereum validators? Now, another a little bit more intricate question is, didn't you find it weird that there was a block every 12 seconds, a copy of the block is received by each one of your nodes, and each one of your nodes has to re-execute the block all over again? Sounds like this is the task that could be made more efficient. And over the past year, a lot of people have been developing zero-knowledge technologies that allows for cheap verification and allow to alleviate this burden from Ethereum nodes. And once you receive the block and you receive the proof for the block, you could just cheaply say that, yes, this block is valid, this block is the new chain head, and I'm going to continue building on top of it. So the future of Ethereum is ZK, and let's talk about how we can get there. So first of all, what does ZK unlock for Ethereum? ZK gives us a way to scale DL1. So it gives us cheap block verification. It gives us interoperability, because once you have a ZK-proven block, you can make small proofs about the transfers or deposits that you have made in this block, and then use it on the destination chain to be able to bridge your assets. And then it gives us privacy. And specifically, it allows you to hide certain part of information about yourself when you're interacting with the blockchain. Now, we have talked about what ZK unlocks for Ethereum, but now let's talk about how to get there. So first of all, and Ansgar touched on this point a little bit already, is we need to restructure the slot. Currently, we do not use efficiently all of the 12 seconds that we have in the slot, and there are a couple more improvements that we can do there. Secondly, we have this term called prover killers. And the prover killers are the expensive opcodes and precompiles that make proven time much higher than it needs to be. And I want to say that some of the gas prices on Ethereum that we have today, they're a legacy of unknown reasoning behind the decisions of how the gas prices were assigned. So now seems like a great time to reevaluate what does each operation actually cost relative to the block processing time. And the third prerequisite are performant provers. As you might have seen, there have been more than 20 different teams working on performant ZK VMs to prove L1 blocks. So now let's look a little bit closer into how to tackle these problems that stop us from making L1 ZK. So first of all is inefficient use of the slot time. Here you can see the current slot architecture. And basically at T0, you have the proposal time where the proposer takes its block, and it can start broadcasting it to the network. And at T0 plus 4 seconds, you have the attestation deadline. What attestation deadline means is that every validator has to receive the proposed block, and it must have validated it by the attestation deadline. As you might have seen in a couple of previous talks, the block processing latency can be as high as 100 milliseconds, and broadcasting it to a large number of validators in the entire world can take as much as well. So it sounds like we could make this more efficient. All right, these are not all of the slides that I have, but that's OK. Now, the slot structure with a proposed ePBS proposal is that instead of broadcasting in that short 4-second window, we start broadcasting the block at the attestation deadline, and we have all the time until this mysterious abbreviation PTC, but you actually don't need to care about it. Consider it just as a broadcast deadline. So you now get a distinct time in which you can broadcast large payloads. Now, the validation can happen all of the time from the moment that you receive the block to the next attestation deadline. So it gives us a way to use the slot more efficiently. Now, I want to take you back to the previous slide for a second. If you were to prove the block, you have to do it once you receive and validate it. Now, essentially, the current slot structure does not give us any room to prove the block. So you might have seen developments from SP1 and how they worked on proving the real-time blocks, proving blocks in real time. What it actually means is they state that they can prove the block in 12 seconds. But this is not enough for the attesters to actually make use of the proofs, because you want the proof to be available at the attestation deadline already. So now in a PBS, your entire proving time, you have the proving time from the broadcast deadline to the next attestation deadline. And the main difference with the PBS is that it actually gives us allocated time to give room for the provers to prove the block. Now, there is another proposal, which is delayed execution, which actually gives you similar properties, where you have time to prove the block from the attestation deadline to the next proposal slot. So the attesters at the next slot can make use of these proofs and cheaply validate the blocks. So this might be a little bit difficult, but one statement that we get all of this is we get allocated time for the provers to use to be able to prove the block so that they can broadcast these proofs to the network, so the network participants can then cheaply verify the blocks. Now, the next boss of getting to ZK-L1 are these mispriced opcodes and precompiles. And there is a lot of great work being done on actually identifying these inefficiencies within the EVM and assigning the proper cost to each one that also accounts for the proving complexity of these operations. And the third boss is actually having the performant provers. And here you can see the list of all of the teams working on different ZK-VM implementations that will make ZK-L1 possible. Now, I hope that you guys will get as excited about this Ethereum long-term future as I am, because when we get zkL1, we will be able to get rid of all of the inefficiencies in the network that we have today. Now, the second part of my presentation is how we can actually make use of the wonderful ZK technology that we already have today on the app layer. So how does L1 privacy look like once we start integrating ZK VMs into our nodes? So first of all, I want to get you acquainted with the concept or one of the proposed solutions of how to hide your identity. So supposedly, an identity is just a random hash or a unique ID that represents you on the network. Now, the way that you can create this random hash is you can derive it from your public key and make a certain salt just to make the identity, just to avoid other entities from mapping your identity back to your public key. Now, where you can use this identity is on the RPC level of the node. You can create specialized endpoints, which I will show you in a second, where you can pass the message that you signed over and the public key, and these specialized RPC methods would be able to prove that this identity actually belongs to the address behind it without actually revealing the address. So what can we do, or what kind of use cases can we implement on the RPC level to make this possible? Now, we could think of something like a proof namespace, which exposes all of these aforementioned methods. And the first use case would be proof token balance. Let's say I want to go to a lender, and I want to tell the lender that I have a certain amount of collateral of the token that I want to borrow against. But I don't want to reveal the address that owns these tokens. How I can achieve that is I can achieve that by creating a proof token balance RPC method that takes as an input the aforementioned message and signature needed to derive the identity, a block hash of the block at which I'm trying to prove that I own the certain amount of tokens, the state root of this block against which I will be proving, and the actual account proof of the account that owns the balance. Now, the only public inputs to this program are the block hash, or the public outputs of this program are the block hash, because the verifier will need to verify against which block the token balance was proven. The derived identity, because this is a unique ID that the verifier will be using to verify that I have an X token balance, and the actual balance that we are verifying. Now, we can take this method a notch further, and we could say that I don't even want to reveal my token balance. I just want to prove to the lender that I have a certain minimal required of the token balances, the certain minimal required amount of the tokens to qualify for this loan. So the only things that this ZK program commits is the block hash, again, to be able to verify against which block this program proved the token balance, and the identity. And the min balance is one of the inputs that ZK program would have to commit to as well. Now, a different use case is proving that your identity has never interacted with a certain X address. The way you could do that is you could build up a ZK program that would prove an execution trace of the transaction. Once you prove the execution trace transaction, you could also assert a statement that this execution trace never accessed the account in question. And the use cases for which this is useful is for something like audits or proving that your source funds never came from a hack or illicit sources. And again, all of this can be accomplished without actually revealing the source, the original address that you are trying to prove. And if we generalize this endpoint even further, we could prove different assertions about the state itself. Let's say I own a maker vault, and I want to go and get it insured, and I want to tell the insurance company that this maker vault has never been liquidated, but I don't want to tell them which one of the maker vaults it is. So the way to do it is I would take a bunch of storage proofs for the slots representing the amount of time, the number of time that the vault has been liquidated. I will assert that this amount of time is 0, and I will broadcast the proof, or I'll send the proof to the insurer, so they would be able to raise my insurance score and give me a better insurance rate. And on the other side, what the verifiers would need is the verify RPC namespace, where they could verify all of these different assertions that the original users wants to prove to them. So I went on a little bit of a tangent, and I thought of how Ethereum privacy pipeline would look like in the future. So first, you have the isolated environment. This is your laptop or your PC where you do have access to your private key. And this is where you generate the either identity proof or identity signature that then you would go to the next step, and you would invoke one of these proof namespace endpoints, either on the prover or on the prover network, that will give you the proof about the assertions that you're trying to make. And then you take this proof, and you go to insurers, you go to the lenders, you go to auditors, and you're able to make different assertions about different state or your funds that without revealing your original identity or the address about which you're making the assertions. I think this is the end of the presentation. The main point that I want to deliver, that the second part of the presentation, all of the proof namespaces, all of the verified namespaces, they're accomplishable today. You can utilize Reth SDK. You can plug in the ZK VM of your choice, which has a usable SDK like RISC-0, like SP1, and you can already expose all of these methods on your node today. Thank you for listening to me. Any questions?
Thank you. So for the RPC of proof no interaction,
yep.
Are all the users' address like shielded? I mean, like, because if everyone else's address is shielded, including the hackers, then how can I generate a proof that I never engaged with just an identity proof that moved the fund?
So not all of the addresses are shielded within the execution trace. What the assertion that you're making with prove no interaction endpoint is that there is some address in the execution trace that the user has a private key to, and it has not interacted with another address in question that the verifier is trying to avoid interacting with.
Got it. So it's so address is not shielded, in short, right? So only the only the proof shows the user's address, right? When you verify the proof, you cannot know my address, but still for this ZKL1, everyone is still storing their funds under plain text address, right?
Yeah, so you're making assertions about Ethereum state as it is represented today.
Got it, thank you.
The only thing that you are shielding is the subject in question, the address that you're trying to make assertions about.
Hi, so
Hi.
how do you see like proof namespaces and ZK EVM like affecting the hardware requirements of like different nodes? And like I know that like SP1 has prover networks and stuff, but if we're plug and playing ZK VMs, then are some like going to end up requiring that nodes like have their own dedicated GPU provers, or will we end up in a world of like delegated proving in order to keep hardware requirements low for our nodes?
The way I would answer this question is it is always about the trust model that you are trying to build. So you would want to run a self-hosted node capable of processing these methods if you never want to reveal your identity to the prover network. But if you feel comfortable with a bunch of random processors to generate the proofs for you, you're comfortable revealing that identity to the prover network, then you can utilize that as well. More concretely answering your question about the node requirements, if you want to run a self-hosted node capable of generating proofs, yes, I think you would have to have a dedicated GPU cluster.
Okay, thank you.
Thank you for your talk. If I understand correctly, the first few slides, eventually the provers are going to become baked in the network, and then you're going to have to reprise some of the opcodes.
Yeah.
Related to one of the earlier talks, which was basically mentioning that you'll have to basically cut the gas price into different segments for like compute data and so on and so forth. Are you thinking of another sort of like gas type segment for ZK specific operations? Because like ZK compute is not the same as normal compute. And also it depends on what kind of ZK VM you're using specifically for the compute.
Yep, I agree. The thing is that when we get to ZK-L1 and we try to generate the proofs for entire L1 blocks, we would have to prove the entire block, meaning that its normal compute, its normal data would all be proven within the ZK-L1. So we're not talking about ZK-specific operations in the VM yet. We're talking about having all of the normal operations that we have today, just being able to generate proofs against them, or proofs of them. And then, yeah, the table that was shown here is which operations that exist today are difficult to prove relative to the amount of gas that they consume.
Okay. Yeah, I guess my question was like, for instance, in a ZK VM, it's much more expensive to do like a store operation than like in real compute life. And like the way you execute the store operations actually influence the cost inside the ZK VM.
No, so actually executing a store operation is cheap. What is expensive within ZK-VM is any kind of cryptography, because there are a large number of mathematical operations that you have to prove.
Okay, thank you.
All right, thank you.